All right, I want to revisit this idea of strength, and I want to look at, is there a way to quantify this? It turns out there is, and the way that we quantify this is with something called the correlation coefficient, and we use the letter R to represent that. Okay? And it actually is going to tell us two things. So it's going to tell us how strong the relationship is just by the numerical value. And then it's also going to tell us the direction. So if R is positive, it means we have an uphill slope. And if R is negative, then our dots are in a downhill trend. Okay, so if we look at this slide, you can see that each of the scatter plots has its correlation coefficient listed below it. So this first one, R is equal to a positive 0.9, and we can see that it's got that uphill trend, which matches the fact that it's positive, whereas the one to the right of it, next to it, says R is equal to negative 0.8. We see that it's got a downhill look to it. Okay? So that correlation coefficient R is trapped between the numbers -1 and +1, so it can't be outside of those. And the closer it is to either a +1 or a -1, the stronger the relationship. The closer it is to 0, the weaker relationship. So if you look at that box in the bottom right-hand corner, you'll see R is equal to 0.1, just kind of looks like a cloud of dust, okay? And that would be that example of not really having a relationship, and then our R is close to 0. All right, so let's go and define exactly what a correlation coefficient is and how that formula works for that. Okay, so a correlation coefficient is a number that measures the strength of the linear relationship between two quantitative variables. Okay, so there are three things that we kind of need to look at before we use a correlation coefficient and do things with it. And the first two are actually just directly related to the definition. So the first is that we have two quantitative variables. So make sure both of those variables are in fact quantitative and not categorical. And then you want to make sure that the data lines up in at least a semi-straight looking form. Okay, so we're looking kind of for that linear form, and that's a little bit of a judgment call. But since this is supposed to measure the strength of the linear relationship, it's helpful if the data is in fact linear, okay, to be able to use that. The last condition is actually related to the formula for this, and this is the outlier condition. So you want to make sure that you don't have outliers because it can really affect your correlation coefficient. So this is like at the beginning of the semester, we talked about if you have outliers or kind of a wonky distribution, you don't want to use the mean and the standard deviation. You'd rather use the median and IQR because they are resistant to outliers. That turns out the way we calculate this correlation coefficient depends on things like the mean and standard deviation, which are susceptible to outliers. So therefore, R is also susceptible to outliers. So let's go ahead and take a look at the formula for that. And actually, before we take a look at the formula, let me put those, I'm sorry, I forgot to advance the PowerPoint to show you those conditions. So let me put those up on the screen for you. And if you need to, you can pause the video and write those down, and then we'll go take a look at that formula. Okay, so one important thing that we want out of a correlation coefficient is that we want it to remain constant no matter what units we are measuring in. So if I was measuring in miles per gallon and I wanted to switch to kilometers per hour, I don't want the strength of the relationship to change just because I used units. That doesn't make it a very helpful measurement. So the way that we deal with that is we standardize each of our variables. So this is like the process we used to find a z-score when we were looking at that. So here's our formula. And you'll see that we've taken the x value, we standardized it, and the y value and standardized it. So you have to do that for every single data point that you have. Okay, and then we have this formula to put this all together. So we're going to multiply all of this mess together and then divide by n-1. We will not be doing this by hand because it is a bugger to do by hand. So we're going to switch over to Excel, and I'm going to show you how to do this in Excel. We're going to look at an endangered manatee example and then does fast driving waste fuel. So let me switch over to Excel so we can take a look at how to do these things. All right, so here's our data set for the manatees. So we have the years listed, I have the boats, and then the manatees. So on your classwork, the first direction says to make a scatter plot using the boats and manatees. So I'm going to do that. I'll highlight both of these. And I'll do insert, and there's my scatter plot. All right, so this looks pretty good actually. I had two quantitative variables, number of boats, number of manatees. This looks pretty straight and I don't really see some significant outliers. I think we're good to go with finding the correlation coefficient. So to get that, the command for that is equals CORREL. Okay, so not the full word correlation, but CORREL. If you start typing it, pretty soon it's the only option there. This one has two inputs, so it says array 1 and then array 2. So they're looking for you to highlight each column independently. And it does not matter which one you highlight first. It just matters that you highlight each one separately. All right, so I have a correlation coefficient, or R, is equal to 0.95. So that's super close to 1, which means this is a really strong relationship. And that's what we would expect from looking at this picture. Those dots are grouped pretty tightly together, so I would expect this to be strong. I would also say it's pretty linear. It's positive, which we know both from looking at the picture as well as the fact that our correlation coefficient is positive. Okay, and I don't really see any outliers. Okay. If you were going to ask me to interpret the direction, so it's a positive direction, which means as x increases, y tends to increase. My interpretation here would be as the number of boats increases, so that would be my x, the number of manatees that die tends to increase as well. So this is our manatee scatter plot, and don't delete this because we're going to come back in a little bit and add a regression line to that. Okay. And then I also want to take a look at fast driving and fuel. So it says, how does the fuel consumption of a car change as its speed increases? There is data for a British Ford Escort where speed is measured in kilometers per hour and fuel consumption in liters of gasoline used per 100 kilometers traveled. Goodness, that's complicated. We're going to create a scatter plot and find that correlation coefficient. So let me switch to fast driving. And I'll highlight both of these. So I have our speed and our fuel. And we're going to go ahead and put in our scatter plot. And oh dear, well, I definitely have two quantitative variables, but this is not linear, not even close. I mean, I kind of have two linear pieces, but that doesn't add up to linear overall. All right, let's go ahead and find the correlation coefficient though while we're here, just to see what's a possibility that could happen out of this. So equals CORREL, and then I'll highlight one of the columns and then the other column. And again, the order does not matter. So I get a correlation coefficient of negative 0.17, so very, very close to 0. So it turns out that if your correlation coefficient is close to 0, it can mean one of two things. So either it means you gave my nieces that bottle of glitter and they threw it everywhere and made a giant mess, so you have no pattern at all, or it's possible that you could have some sort of curved pattern that kind of, the way that the formula works, these two kind of get canceled out, so you end up with a number close to 0. Okay, so that is a possible result out of there. So just because it's 0 doesn't mean that there's no pattern at all, but there is not a strictly linear pattern there. All right.